Hey math fans, Alex here, and welcome to our last video on generating functions. So to start off with, let's go ahead and find the generating function of just a Bernoulli random variable. Okay, so it should be pretty easy. So we're going to go ahead and let xi be Bernoulli. And remember, the only parameter we need for a Bernoulli random variable is p. And I'll go ahead and give you the PDF. I'll remind you that the PDF for this was... It's basically either p for, we'll say k equals 1. We'll deem that a success. And we'll say it's q otherwise. So maybe k equals 0. So we'll say that 1 is a success and 0 is a failure. So we're going to go ahead and denote it like this. Okay. Well, then the generating function, according to last time, is going to be a xi of z, which is going to be the sum from k equals 0 to infinity of the probability density function evaluated at k times z to the k. Okay, but we're really not summing from k equals 0 to infinity because k only takes on two options there. Okay, so really what we have is that this is going to be the sum from k equals 0 to 1. So I'm going to go ahead and just evaluate that for you. So first off, we're going to have p if k is equal to 1 and q if k is equal to 0. Okay, so we're going to have q z to the 0 plus p z to the 1. Okay, which evaluates to q plus pz. Now that's interesting, right? Because last time we talked about a very similar looking generating function. So I'll just kind of make a note. But wait, isn't a, x of z equal to q plus pz to the n for x, the random variable, being the sum from, we'll say, I equals 1 to n of the xi's. Okay, and remember that if you sum a bunch of Bernoulli random variables, then that has distribution of the binomial random variable, this time with parameters n and p. So that's very interesting that if we take this generating function and then we take the generating function of the sum of those, we actually, it looks like we get the product of those. Okay? And it turns out that that's no mere coincidence, and we're going to kind of talk about why. Okay? So it appears that the generating function for, we'll say, x1 plus ... plus xn of z looks like that is the product of generating functions for random variables x1, x2, and so on until xn of z. That's what it appears, at least. And I'm not going to really give you a formal proof. I'm really just going to demonstrate it. This is going to be kind of informal. This result does hold. And here's kind of why. So remember that ax of z looks something like this. So it's k equals 0 to infinity of p x of k times z to the k. So I just want to kind of turn your attention for a second to this quantity right here. So k is an element of the is a member of the random variable x. Okay, as such, what we can actually say is that this is equal to the expected value of z to the x. Right? just kind of think about what that represents. How would you write the expected value of z to the random variable x? Well, you would sum from all possible values of z to the k times the probability density function. Okay? So we're going to kind of use that to justify the claim above. So it follows that if I take maybe x1 through xn of z, by the same exact logic, that should be the expected value of z raised to the x1 plus ... plus xn power. But using kind of the power rule, this is equal to the expected value of z to the x1 times z to the x2 times ... times z to the xn. And we have to assume, for this next part, that all of the random variables are, you guessed it, independently and identically distributed. Mainly independent, right? The independent assumption allows us to multiply the expected values. The expected value of a product is thus the product of the expected values. Okay? And each of these expected values is just the generating function of that random variable. Okay, so there we go. That's kind of a proof of the claim. Now, of course, the story is a lot more complicated. For example, if z is a complex number, which we're being general and allowing it to be complex, why is this equal to this? I mean, and do the random variables have to be independent? Can we loosen that restriction? But I'm just going to go and cut the slack and say that this is not a coincidence. This relationship right here, yes, if you sum a bunch of Bernoulli random variables with this generating function, you can just multiply them together. And the reason that I'm making such a big deal about this is when we talk about characteristic functions, it's going to have a very similar relationship, and we're going to use that for the proof of the central limit theorem. Okay, so in other words, so conclusion, I'll say, for x equal to x1 plus yada yada plus xn, we have that the generating function for x is really the same as the product of generating functions. And of course, sometimes you'll see the product symbol is just a big old pi. So you'll see that, maybe from I equals 1 to n of a xi of z. So there we go. Okay. Now, the last thing that I want to talk about generating functions is one more small application, and it's one that we've seen before in a problem that I assigned to you. So let's go and take a look at that. Okay, so here's the problem. It says, let P be the probability of success in a series of Bernoulli trials. What is the probability capital P sub n of an even number of successes in n trials? Okay, so for example, if you're flipping a coin, heads and tails, and whatever your sample size n is, since all the probabilities of heads and tails are the same, you would guess that getting an even number of successes is the same as getting an odd number of successes. Okay, so that probability works out to be 1/2. But if it's, say, a weighted coin, or if the probabilities aren't the same, this is a very non-trivial question. Okay, so this is chapter 5, number 4. And you can see the 3 stars means that it's a doozy. So I'm going to go and refer you to this video to get to the following point, so you can inductively establish that capital P sub n, which is what we're trying to find, is actually going to be equal to capital P sub n minus 1 times the quantity 1 minus 2p, lowercase p, plus lowercase p. Okay, so I should just say see chapter 5 review video. I might put a link to that like right here-ish. Sorry, I'm new to YouTube. Okay, here we go. Now, the first way that I solved this was using something called a difference equation. So I should maybe write that down. And that is not to be confused with a differential equation, although the methods are very similar. You had to solve the homogeneous difference equation, then the non-homogeneous difference equation, and then take a linear combination of solutions. So that was kind of a mess, honestly. So I'm going to show you method 2, which actually relies on generating functions. So I love math for this very reason. There are so many different ways to solve the same problem. Is this way easier? It relies on stuff that we've seen. Let's just leave it at that, okay? So basically the goal is to solve this kind of recursive equation somehow. And the way we're going to do that is we're going to somehow come up with the generating function. Okay, so let's go ahead and do that. And what I'm going to say is to get the generating function, first thing we're going to do is, well, we need a z to the n, right? So we're going to multiply everything by zn, and then we're going to sum from 0 to infinity. Okay, right? Because remember that ax of c was the sum k equals 0 to infinity of the probabilities, so namely that. So we could even just say p sub k times c to the k. And maybe I should, you know, can make a joke about me being so bad about going between n and k. Let's just use k and see what happens. I'm sorry, I used n in the previous video, but let's just use k. Let's see what happens. All right, so we're going to multiply by z to the n, and then go ahead and sum from k equals 0 to infinity. And let's see what happens there. Okay, so when we do that, we're going to get the sum from k equals 0 to infinity of pk z to the k. Okay, and that's going to equal the sum from k equals 0 to infinity of pk minus 1 times 1 minus 2p. Okay, z to the k, plus the sum from k equals 0 to infinity of little p times z to the k. Okay. Now, I'm actually looking at this right now, and I'm seeing that we actually can't really sum this from k equals 0 to infinity. The reason being is this right here, right? This starts at k equals 1. This has to start at k equals 1. So now I'm going to amend what I said earlier, and we're actually going to start from 1. This is not going to be a true generating function yet. We have to kind of add that k equals 0 term in, but I'm going to show you how we can do that. Okay, so trial and error, basically. All right, so k equals 1. Let's see what happens. So what we have here, do this in blue perhaps, this is almost the generating function. But we're ignoring that k equals 0 term. What would the k equals 0 term be? Well, the k equals 0 term would be p0 z to the 0. Okay. But p0, if we kind of look back to kind of what this is, even number of successes, right? So if I have 0 trials, what's the probability of an even number of successes? Well, that's 1, because 0 is an even number. So that's just defined to be 1. Okay, so this kind of adds in the 1 if we include the generating function, which means this term right here is almost the generating function. It's almost the generating function, but we have to then subtract 1 from that. Okay. Okay, so that's going to equal, let's see, I'm going to factor out the 1 minus 2p. Then we have this sum from k equals 1 to infinity of p k minus 1 z to the k plus this term right here. I'm going to go ahead and factor out a p. And what I'm going to do, oh, nothing. Let's just do nothing for now. Okay. So z to the k. Okay. Now what I'm going to do is I'm going to go ahead and factor a z from both of these terms. You're going to see why in just a minute. So if I do that, then I get that ax of z minus 1 is equal to 1 minus 2p times, and then I'll factor a z out, and then I have the sum from k equals 1 to infinity of big P k minus 1 z to the k minus 1 plus pz times the sum from k equals 1 to infinity of z to the k minus 1. Okay? Hopefully we're with me so far. Now, that's kind of interesting because this term right here is just the definition of the generating function. Right? So we can go ahead and include that now. And this is a classic geometric series. Right? Because k minus 1 and k equals 1, it's shifted essentially. And if you write out the terms, we are now summing starting from z to the 0th power plus z to the 1st power, z to the 2nd power. So we are including all the powers. So I can, if you need to rewrite this as from k equals 0 to infinity of z to the k, you can do that, but I think it's pretty clear that this is just shifted a little bit. Okay, so this is just geometric series, which is 1 over 1 minus c. Talked about that in the previous video, so let's put everything together now. So we get that the generating function minus 1 is equal to 1 minus 2p times z times the generating function of c, or for x, plus pz times 1 over 1 minus c. So that's going to be pz over 1 minus c. Okay. Now I'm going to go ahead and subtract this over and then factor out the generating function. Okay, so I'm going to get that the generating function, and after I factor that out, I'm going to get a 1 after I factor it out here, and then a minus, because I subtract this over, minus all this junk. So I get 1 minus 2p z. Okay, minus 1 is equal to pz all over 1 minus z. Now what I'm going to do is I'm going to add 1 to both sides. So I'm going to add 1, and then I'm going to divide by the 1 minus 2p times z. Okay. All right, so what do we get? Well, we get that ax of z is then going to equal 1 over 1 minus 2pz. And that's just from the plus 1. And then I have pz divided by 1 minus z times 1 minus 2p times z. Okay. So the algebra is going to be the hardest part of this. I'm going to be really honest with you. So what we're going to do next is we're actually going to so what we're actually going to do is we're going to do partial fractions on this. Okay? So the way that, usually you do partial fractions, I have a trick for that. So the idea is, maybe I should kind of do this off to the side. So if you have something like 1 over z minus a times z minus b. The trick is you want to write this as, some constant here divided by z minus a plus another constant divided by z minus b. So the trick is plug in z equals a everywhere, just everywhere. But when you do that, you're going to get an undefined here, so you have to kind of cancel this out, like cover it up with your hand, and then plug in z equals a. That's going to get you this coefficient. So this coefficient is actually going to be 1 divided by a minus b. Okay? So now what you're going to do, is you're going to do the exact same thing, right? The exact same thing. So this is still z minus a times z minus b. And this time you're going to plug in z equals b, but kind of cover that up with your hand. And that gets you this coefficient. So this coefficient is going to be 1 over b minus a, which is really the same thing as, okay, well, it doesn't matter. But that's how you find the coefficients. It's kind of a shortcut. It's really not a shortcut if you kind of look at complex analysis and whatnot and poles and all that fun stuff, but it makes sense. Okay, so I'm going to use partial fractions. Okay, so I'm just going to maybe make a note. So partial fractions. Let's do that. Let's just kind of see what happens. So maybe I should kind of box that off, and we'll kind of do it to the side here. Okay, so first thing I'm going to do, I want to break this up into some term divided by 1 minus z plus some term divided by 1 minus 2p z. Okay, so remember what I told you. So the first thing we're going to do is we're going to take this entire expression and plug in z equals 1, but ignore this part. So ignoring this part and plugging in z equals 1, we get p times 1 divided by 1 minus 2p times 1. Well, that just gets us a 2p. So that's that coefficient. Okay? So now, I have to rewrite this, but that's okay. Now, we're going to plug in the thing that would make this equal to 0. Well, what would make this equal to 0? We can just solve it really quickly. Well, that would be 1 divided by 1 minus 2p. So that's what we're going to plug in for z. 1 over 1 minus 2p. Okay, so we get p times 1 over 1 minus 2p divided by, and remember we have to kind of cross that out from your head, 1 minus z. So that is going to be 1 minus 1 over 1 minus 2p. Okay. Yeah, I know. It's kind of ridiculous, but hey, you signed up for it. Okay, so the first term is pretty easy. That's just going to be a half divided by 1 minus c, or a half times 1 over 1 minus c. This term is a little less straightforward, but let's just try to write it out. So this is going to be 1 over 1 minus 2p z times this junk. Okay, but I can write that as p over 1 minus 2p on top, that's this term, and on bottom I have 1 minus 1 over 1 minus 2p, but if you write this as a common denominator, well, let's just do that. So this is going to be 1 minus 2p minus 1 all divided by 1 minus 2p, but the 1's cancel, and we're left with a negative 2p. Okay, so this is a negative 2p. Okay, so we have that fraction divided by that fraction. We're going to need to take the reciprocal of that to kind of simplify that, or better solution, just cancel the denominators out like that, and then we have p over negative 2p, and then the p's cancel, and we're left with negative 1/2. Okay, so we get that this is 1/2, 1 over 1 minus c minus 1/2 times 1 over 1 minus 2p z. Okay, so this is all kind of like off to the side. In my opinion, that's kind of the trickiest part of this problem, but now we can kind of finish her up. So we have ax of z, the generating function, is going to be equal to, we still have this first term. Don't forget about that first term. So it's going to be 1 over 1 minus 2pz. And then we have plus 1/2 1 over 1 minus c minus 1/2 times 1 over 1 minus 2pz. Okay. Clearly these are like terms. We have a 1 times this crap minus 1/2 times this crap. And we get positive 1/2 times this crap. Okay, so we get that the generating function is 1/2 1 over 1 minus c plus 1/2 times 1 over 1 minus 2pz. Okay, that is the generating function of the random variable. I'm tempted to box this answer, but I can't because we need the probability. We need the probability of getting so many successes. We need capital P of k. So we just want the probability. And to get that, remember one of those properties, which I'll just kind of remind you. So recall that if you want the probability of getting k successes, remember that's the probability that x takes on k, probability generating function says that you have to take the kth derivative of this, evaluate it at 0, and divide that by k factorial. Okay, now, sorry, just in advance, I'm sorry. Not going to really kind of verify that for you, but this is kind of, if you repeatedly take the derivative of this, and if you repeatedly take the derivative of this, you're going to sense a pattern. Okay, and that pattern is going to show you that pk. So we're going to kind of take the kth derivative of this and evaluate it at 0. And what you're going to find is that here, when you do that, you're going to spit out a k factorial. So this is essentially a 1/2, which kind of goes in front. And then you'll have a k factorial from taking the derivative k times and evaluating at 0, divided by k factorial. That's just, again, from here. Plus, and then you'll still have this 1/2. But this time when you take the derivative, it's going to be the same thing, but chain rule, right? So that's going to cause this to pick up a 1 minus 2p to the k, whatever that is. Okay, so, and then times k factorial divided by k factorial. Again, thankfully, these are both 1. So then finally we get that pk, after factoring a 1/2 out, is 1/2 times 1 plus 1 minus 2p all to the k, which agrees with the answer that we got last time. I don't know if this was easier than the difference equations, but I at least think that this is more straightforward, easier to follow, and beautiful because it's based only off of stuff that you've presumably seen up to this point. Okay, so that was that problem of finding the probability of an even number of successes in K Bernoulli trials. Hope that was helpful. Have a great rest of your day.